Okay, so in this second video, I'm going to discuss coarse grain synchronization. We're going to actually have a look at the code. So yeah, let's jump straight in. So this one, like I told you guys, coarse grain synchronization kind of has a problem, right? If we have a single thread that locks the entire linked list, we kind of run into a problem because now things are basically operating sequentially at this point, because if only one thing is working on the linked list, let's say only one thing is working, let's say over here, and let's just say this isn't actually the tail. Let's say only one thread is working on this entire linked list. Let's say it goes on and on and on. If only one thread is working over here, it actually prevents the other threads from actually doing anything on the rest of the linked list, and so we're actually losing out on efficiency, right? Our system could be more efficient, but because we have this system that only allows one at a time, we kind of run into an issue. And so that's why we're going to have a look at other ones. But let's actually first understand coarse grain properly. So we're going to have a look at the add function of coarse grained and then at the remove function. So let's have a look. Here we have the coarse list class. We have a node, which is defined as I showed you above. And we have a lock, which is a reentrant lock. Reentrant lock, for those who don't know, is just a lock that allows the thread that's currently holding the lock to access that lock again, or to get the lock again without blocking. And it does this without like any deadlocks or anything like that. But yeah, so here we have the constructor. This just creates the head and the tail. So what's happening over here, it just says head with the smallest possible integer value, and then it makes it point at this, which will actually be the tail. It will be pointing at null, but we'll represent null like this. And this will just be the largest possible integer value. This is such that it's always going from obviously lowest to highest, ascending order. Like we said, one of the invariants of the linked list is that it always has to be sorted by key, right, in order for things to work. So let's actually have a look at the adding function. So we declare these variables predecessor and current, and then we declare this variable key, which just comes from the items hash code. So like we said, we're going to just find a place in the linked list where that particular key will fit. Not like I said, sorry, but in this case I'm using these numbers here to represent the key. They're not actually representing that value t, like I saw here. It's not actually representing the item in this case. I'm just using it to represent that. So yeah, just to avoid any confusion. So we have predecessor, and then we have current defined. You see here, predecessor is equal to head, current is equal to predecessor dot next. And we can do this because we know that there's always at least two nodes in the list, whether it's just the head and the tail, or more, there will always be two or more nodes in the thing. So that's why we can do this. Then what we're going to do is we're going to iterate until the current key is no longer less than this key, the key of what we want to add. So over here, let's just start. So we see, is current key less than the key you want to add? So we're asking, is 1 less than 2? Yes, 1 is less than 2. So now we're going to enter into this loop, and we're going to do what it says. So predecessor is equal to current. So make predecessor point at current. You can hear that I learned C++ first, because speaking about pointing and whatnot. But anyways, yeah, pointers and what. Anyway, so yeah, that one's pointing there, and then current is equal to current dot next. So it goes here, and yeah. Then now we're going to do the comparison again. In reality, you might actually need to. Actually, no, never mind. You won't need to. You're gonna do the check again, and then, like we said, this is the smallest possible integer. This is the highest possible integer that's represented in Java. So that would be the highest possible represented by 4. Actually, let me not get into irrelevant things. And I'm not even sure if that's the case in Java. But yeah, in any case, so now we compare this to 2 and realize that 3 is not actually less than 2. And so now we're going to have to exit this while loop. And now we exit it, and now it says if key is equal to current.key, which would be the case when, let's say, we wanted to add 3 to the thing. So if it already exists in the queue, sorry, not in the queue, in the linked list, now we have to return false, because remember we said that's what the add does. The add is a Boolean function, and it returns false if it already exists and true if it was added successfully. So yeah, otherwise, so if it does not already exist in the linked list, now what we're going to do is we're going to take this value and we're going to put it into, or rather that item. I'm going to take that item and we're going to put it into a node. I'm just going to put its key here. In this case, we said it's 2, and it's, I believe the constructor should start with it being, with it pointing it null, or with this next value being null. And then we say now the node.next is equal to current, and then pred.next is equal to node. So let me just redraw this neatly. And so I've redrawn it, and we see that we have now added this node to the linked list. As you can see, this is very basic, very similar to the basic linked list, except you have the lock over here, we have the try finally, and then we have to unlock. Obviously, this is just following the basic format whenever you use a reentrant lock. Goodness, I can't spell today. But yeah, so now onto the remove method. So over here we have the remove method, and the way the remove method works is that it returns true if it removed it successfully, and it returns false if it did not, if the item we were looking for in the linked list did not exist. So yeah, so the way you're going to start off is the same as the previous one, and then we're just going to lock the lock, and then here's the beginning of the try finally block, and we're just going to set predecessor to head and current to predecessor.next as we did in the previous example. So now we're going to iterate while current.key is less than key. In this case, we want to remove 7. We have 5, 6, 7, 8. Anyways, so while current key is less than key, in this case current key is 5, and 5 is in fact less than 7, so we continue with the loop. We say predecessor is equal to current, and then current is equal to current.next, and then we check the condition again, and then 6 is less than 7, and so what we're going to do here is set predecessor to that one and current to that one, and then we check again, is 7 less than 7? No, 7 is not less than 7. So we're going to exit the loop, and in this case here we check whether the key is equal to the current key, and in fact 7 is equal to 7. What a shocker. And so let's actually think about what would happen if, actually we'll get to that case now. But yeah, so 7 is equal to 7, so we're going to set predecessor.next to current.next. So that's we're going to do that by doing this, and yeah, and now thanks to Java's garbage collection, this just gets removed. It's not like C++ where you have to say delete. But yeah, so this is what the list looks like now that we've removed that, and mission complete. And then obviously we have to unlock in this finally block as you usually do. So what would happen if we iterated through the whole thing and we didn't find it? So that would be a situation where we have, let's just redraw these. What would happen is that it would go predecessor. Let's say we wanted to remove 9, right? So we would say is current key less than key. 5 is 5 less than 9. Yes, 5 is less than 9. So you're going to go here, move that one. Now we ask, is 6 less than 9? Yes, 6 is less than 9. So you're going to move this one here, and then move this one here. Then you're going to ask, is 8 less than 9? Sorry, I don't know why there's a number here. There shouldn't be a number there. Actually, that number should just be the highest possible integer. This one is the lowest possible integer in the head, the highest possible integer that can be represented in Java, in the head and the tail. Okay, so yeah, so we say, is 8 less than 9? 8 is in fact less than 9, and so it's gonna go here. Then this one's gonna point here, and then is this number that is in the tail less than 9? No, because remember we said that it's the number that's in the tail is the integer max value. So that's going to be some really ridiculously big positive number. I'm just going to put some random big number, right? It's not actually going to be that, but yeah. But it's always going to be greater than, I guess, or equal to that. So it's going to, so that just means it's not going to be less than. So it's going to, at that point the loop is going to end. And then it's going to check, is it equal to, and since it's not equal to 9, it's just going to return false, and then it's going to unlock, and that's going to be the end. I hope this makes sense to you. It's not very complicated if you already have an understanding of linked lists. Like I said, I think I said in the previous video, I should come up with a video with that, but yeah. So I hope that all makes sense. Catch you guys in the next video.